Hello, I'm Thomas Olson, and I want to talk to you about the Eisenstein Triples. What I really want to talk to you about is the Mandelbrot set, but we got to start with the Eisenstein Triples. I'm going to be making Eisenstein Triples into this Mandelbrot set, and I'll be skewing the Mandelbrot set with it. I should probably mention that I ripped this code off of Zacer. It's from Mandelbrot Explorer. Here's the author right here. X-Acer. So back to Eisenstein Triples. Eisenstein Triples are based on cosine law. We got alright, so this here, you could put in a value. This is cosine law, so we want to put a cosine in there, a cos of 60 degrees, which ends up being 1/2. It's a nice rational value. I suppose if you wanted to, you can put anything in there, but you're probably going to have a pretty messy situation going on. Anyways, let's do this. Alright, simplify it. Get rid of the 2's. Put this over here and minus. Take this C and we'll put it on the other side. So we got this a squared. We turn these the a and b into an x and a y, I suppose, and there you have it. I mean, if it was a 1/2, why don't we just try 1/2? Alright, so the cosine of 120 degrees is negative 1/2, because 120 is double 60, and you got the cos theta, 2 cos theta thing, which is 1 minus 2 times sine squared theta. So 1 minus 2 times square root of 3 divided by 2. Since it's squared, the square root of 3 becomes a 3, and the 2 in the denominator becomes a 4. So there's two 2's that cancel. So you got 3/2. 1 minus 3/2. That's negative 1/2. All right. And this becomes a plus. There you go. So it's both, essentially, and plus and the minus, they don't really matter. I guess it depends which number is higher than the other, A or B. That's what will really change what the angle is. So let's do this little one here. 387. 587. All right, 3787 and 1. All right, so this will work because it's a scalar. Scalars still work on ellipsoids. Okay, is that a 3? I can't even see what that number is. Let's just change this to a 5. Maybe I could solve something here. Alright, so that looks like a 4. That's 7. Sine of 120 minus 1 divided by 7. We can verify that right now. Alright, that's right. Okay. So let's do this. An example of this real quick. So 4 divided by 7, all that times sine of 120. So we're doing a sine of alpha minus beta. That's sine alpha times cos of beta minus cos alpha times the sine of beta. So the sine of alpha here would be square root of 3 divided by 2. That's the y value of that. It's still in the upper quadrant because it's 120 and it's below 180, so it's still in the upper quadrant. It's positive. And I guess we got to do the cosine of 1/7, which is just right there, 1 divided by 7. Don't have to do much there. As for the sine of 120, that we already talked about that. That's 1 divided by 2 times. And well, this is a little bit more trickier. We have to do a square root of 1 minus 1 divided by 7, and we have to square that. And there we go. That's your exact value. 0.353479 blah blah blah. I like these 10 divided by 49 times the square root of 3. It's much better that way. Do your math. Don't do this decimal crap. Alright? Okay, let's talk about my functions. My Eisenstein functions. Eisenstein. Alright, we got 4 functions here. F of x, f of y, g of x, g of y. The f's are the minuses. X squared minus xy plus y squared. That's the 60 degree, which, as I said, they're not 60 degrees. And then there's the g functions. The x squared plus xy. It's got a plus right here instead of a minus, which is the 120 function. And I put in x and y to simulate cos and sine. Cos being the x, sine being the y, kind of thing. There isn't an angle system in place for the ellipse that I know of. Maybe there is. It'd be cool if there is. Anyways, what we have here is a binomial function right here. We got a sum, and we got kind of unit vector kind of thing, looking things here. The thing is with the complex plane, you don't need to make things into a unit vector to figure out angles. The radius just goes out of control, and you keep it, and that's why the Mandelbrot does what it does. It explodes or it doesn't explode, and you assign a color. This unit vector, it keeps it in proportion. Alright, so the Eisenstein functions. I should at least do around sequences for this. We'll just do 2 right here. We'll need to simplify. And k is equal to 1.6. It goes 0, -1, 1, 0. So we multiply this by 0, and this k in the sum, it just goes poof. It's no more. Don't count the sum. Then on the next one, it goes -1, right? And just makes everything -1. And then they go 1, and it's a 3-number cycle. I'll keep doing that. I'll do that forever, no matter how high it gets. How did I find it? I think it was the solutions to x squared minus x plus 1. Let's give that a try. That's probably it. Yeah. That's for this one right here and this one. Or this one, that's for the g functions. And that's a different solution. I don't think it matters. I don't need to talk about that. I did a paper on that, but it's not really needed here. Okay, so we can actually make an ellipse out of these functions. I'll have to do a 3D plot to show you. We go f of x, and we want to, well, let's start with 1. X, y, f of capital Y. We'll have to do capital X here too. And 1x and y. And we'll need to put a 0 in here. It's a 3D plot, and Maple doesn't have a 2D. Well, they might. I don't know if actually I think they do, but I would have to be messing around with a complex plot. Okay, x is equal to -10 dot dot 10, y is equal to -10 dot dot 10. We can actually put in an exact number of points. So we're going from -10 to 10. There's a 0 between those two numbers, so that's 21. And 21 squared would be 441. Let's do 441. Alright, see, there's a problem here. If I were to do this, it would have to calculate this every single time. So let's not do that. Let's just simplify this. Yeah, that's not very impressive, is it? But we get a nice little sum here. Can put in the lines, I suppose. Nothing really interesting there. There's so many points that it looks like a straight line, but it isn't. Okay. If we keep these the same, it'll always be a sphere, or it'll always be an ellipse. But if we like change that to a 2 and change this to a 9 and do a simplify, we'll get something. I'm not sure what we'll get. It's a lasso figure, except it's not really one. The spaces between these diamonds should all be pretty much equal up until the half. They don't quite look equal. Maybe they are. I don't know. Who cares? Anyways, let's do a spherical kind of thing. You got the sphere. What is it? Cos A times sine of A times this cos. Actually, that's not really the function, but that's not the official function, but it kind of does something like that, right? If you do the square root on these two here, this cos A and this cos B, they go poof, because it's just what happens. Alright, let's do this here. So we got a f of x, we put an f of y2 here, we'll put it 1 here too. And then we'll put another f of x, and we'll make that a 4, or how about a 6? We'll make it a 6. And we'll do f of y to the negative 6, and we'll simplify that. Alright. So we got a loop here, and well, what we have is a 2 and a 6. So if we did this with the circular functions that are like this, that we use in the Mandelbrot, we get the same thing, except in this case it's skewed. Let's go to the normal functions here. So we got one of these and 2 of these. Alright, and the next one is 6. We need a 6 of F. Well, not of F. Right here. Whoops. Alright, so this would be like cos, and I put cos, that's x, it would be like x. Put that in there, and this would be like y, f of y. And we put these in here. Let's copy this. Let's see if they look alike. Oh, look at that. That's just too many points. I'm just going to delete that, but you get the point, right? Hopefully. Aha. Any moment now I'll be able to delete this. Let's delete this one too. We don't need to do this anymore. We're done. Screw that. Alright. So we did the functions, we talked about the sum, the binomial, those two things, Laplace, we got De Moivre's, forget it. Alright, De Moivre. We got this function here, just like mine, and same thing right here, just like mine. We got the n, k, n minus k, we got an x and a y, and we got a function here, killing values. It's pretty much exactly the same thing as this rotation matrix. The rotation, cos, sine, negative sine. Now if you want to make this into this, you put this square root here in where the y is supposed to go, and you can make it into a three-dimensional function that we use in the Mandelbrot set, or I should say the Mandelbulb. To do that, it's a trick though. So you put that in there, and you got the square root right here. It's the distance function. But that doesn't make much sense, does it? How about if we put a y there and a z there? Now let's look at the sphere all by itself. Okay, you got the sphere. Those are the numbers. Let's dial it down a notch. We'll do -5 to 5. So we're actually doing 11 cubed points. We reduce the points. We can actually see what's going on here. We got this little circle. We got this little circle. Well, not circle, but all the same circle, same size, radius. But we got all these circles coming, and that's how you should be looking at this stuff. The circles are forming because because of this rotation matrix. This distance of y squared plus z squared in a two-dimensional rotation matrix. All the points are just put in there, I guess. The higher this number goes, the more points you get like that, and the space fills up real quick, so you can't really see it, but you can see these circles, some circles. Anyway, why don't we look at some more interesting functions like this right here. This is a Smith something or other. I don't know what it's called. A Smith graph. They use this in to measure wavelengths or something like that. At least I think that's what it is. It kind of looks like it. You can actually go in there. Never mind. Alright, so we talked about these. So right here, these are the functions that end up in the Mandelbrot. X squared minus z squared minus z squared. And these are the numbers where they stand on, I guess, in a unit cube. And these are other variations of that. I can't remember what they were, but these are not one-to-one. Okay, so I copied that to there, that to there, that to there. The square root becomes a y and a z sort of thing. And we repeat that for n or z to whatever we're doing. Z to the 6th. I could show you z to the 6th or z to the something anyway. I made a whole bunch of spin-offs on this guy's code. What's this right here? That might be a 6. That's Z7. Close enough. I don't know if you can see that. We'll find out. So I think I talked about everything. Or not quite. Let's go back to the original, and we'll go to the Mandelbrot two-dimensional version. Alright, so we go down the code here, and just change this to an x1. Actually, let's I can do y1 times y1 right here, and that will get us a quick skewed Mandelbrot. But here's the thing, if I do this alone, X1, X1. I just get a plain circle right here, right? So I do have to manipulate the radius. It'll have to be X1 times Y1. And then we got the ellipse again. I can also add that. That's the 120 degree. We'll start. And I can do the other variations on this. There's Z2. This is Z2 on the Mandelbrot. And I have Z1 right here. Again. I just clicked on that just so I can get to the next one. I think this was Z4. Yep, Z4. And it's skewed just like the other ones. And if I can figure out how to do the ellipsoid version, this y squared plus z squared trick will probably work in some way. I think it does. I've done this before. It's been 5 years or so since I've played around with these things. I didn't know about Mandelbrot or Mandelbrot 5 years ago, though. Specifically ellipsoids. Anyway, you know what? That's enough for now.